Thanks, and thanks very much to the organizers for putting together such a nice workshop in these circumstances. I've certainly learned a lot. I wish we could all meet in person, but that's for the future. Please let me know if you can hear me fine or not, and I'll adjust. So my talk is a little orthogonal to the theme of the previous talks on large charge. So the only thing that will be potentially large in my talk will be large n or large spin. But in the end, we're all after the same type of data. So I'm just approaching a different subset of the theory from a different angle, and hopefully we can bring things together and improve like this. So I will try to give you an overview of what we can do with this, and I will do it focusing on a theory that's very close to my heart, which is the 6-dimensional n equals to SCFT. So if you don't know what it is, I will say a little bit about it. So this is the outline of my talk. I will start by a brief introduction on what are the main highlights of this approach. Then I will review some work that's not supersymmetric, and it's also not my work. It's the inversion formula of Simon Caron-Huo. And then I will be applying it to 6-dimensional series with maximal supersymmetry. And the reason for that is that the supersymmetry gives me an extra handle, an extra control on the theory. So as you will see, the niceness of supersymmetry will bring in a way where I'll be able to describe the Regge trajectories of this theory all the way down to spin 0 and even beyond. And it also gives us an opportunity to try a wildly optimistic approach of trying to bootstrap the spectrum of the theory, and I will show you some preliminary results on that to try to not bootstrap in the traditional sense, but try to get something out of nothing in that sense. So I've been saying a lot of words, so let me start by giving some more details of what I mean. So the idea of this talk, the name Regge Trajectories, it comes from what we learned to expect from the work of Simon Caron-Huo, that the CFT data organizes itself in trajectories, in Regge trajectories starting at spin 1, by which I mean that the dimensions of the operators are expected to be smooth functions of the spin, and similarly the OP coefficients are expected to be smooth functions of the spin. And I'm saying expected because there are some little caveats that you can ask me about later if you want to know more. But what Caron-Huo has shown us, and many people have used so far, is this idea that if you you can draw this picture. It makes sense to draw a picture in it makes sense to draw something like this, where I can plot the dimension, and for simplicity, I'm putting a shift by d half for the dimension of space-time versus the spin of the operators, and I can draw trajectories, and these are Regge trajectories in this space that interpolate between my operators. So I would have here an operator of spin 0, an operator of spin 2, say, and so on. And these operators are not randomly scattered, but they actually lie on trajectories. And I highlighted here, this is for spin bigger than 1. So actually I should not be allowed to, I'm not sure what happens below here, but at least for spin bigger than 1, operators should be organized, should fit into these smooth functions that we can draw. And now comes in supersymmetry, which is which then has supercharges that relate operators of different spins. And so in particular, for the theory I'm after, the 6-dimensional theory with n equals 2 supersymmetry, supercharges will relate operators of spin L with operator spin L plus 4. So naively, you would expect that you'd be allowed to draw this picture like I did, going below the spin 1 that Simon promised us by using this basic fact. This is a bit of a naive argument. We have actually, yeah, please go ahead.
Just for clarification, what do you mean by when you say spin L in 6 dimensions? What is spin?
Because I will be looking at, thanks. So because I will be looking at the OP of 2 scalars, then I will have a symmetric traceless representations. And this is what I'm meaning by L.
And what you're going to say in these Regge trajectories only apply to these symmetric traceless representation?
Yes and no. So Simon's work was originally for the 4-point function of 4 scalar operators in any dimension. So then scalars exchange always symmetric traceless, and this is what his work was about. Then people have extended this work for external operators with spin, meaning that they start to exchange other representations, and similar stories hold. It just gets practically much more convoluted because of all the spin indices. So it's work by David Simon-Steffin, Petr Kravchuk, and Sasha Zhiboedov as well. So my work will focus on these operators because they're the ones that are exchanging this OP, which is what I'm probing. But this structure, this inversion formula, which I will review and will give us the structure, is there for other OPs as well.
Okay, thanks.
And then, so as I was saying, supersymmetry will bring down the regime in which we can expect this trajectory, the operators to lie in this trajectory down to lower spin. In my particular case, of 6T that we looked at with Balt and Shang, it actually brings it down to spin -3. You might think I'm exaggerating by writing a negative spin, but we'll see how negative spins play a role in a little bit. So this argument I gave was a little bit too naive. You actually have to show it based on how the correlator behaves in a certain limit. And so this statement depends a bit on the amount of SUSY, but also on the particular correlator you're looking at. And I can comment on other cases if people want. And then the other, so this is one reason we were driven to look at supersymmetry, because now we can actually try to understand the spectrum as a whole, and we're not restricted to spin greater than 1. And then the other nice thing about supersymmetry is that we end up having some exact results. So there are often protected operators whose dimensions we know, and sometimes we even know the OP coefficients of these operators exactly. So this is some sort of starting point from which we can try to construct or attempt to bootstrap in optimistic, hopeful ways the spectrum. So I will focus on this 6-dimensional theory, but a lot of what I say will apply also to other dimensions and other amounts of supersymmetry. So you can ask me a little bit about that if you want. In particular, this type of analyticity down to lower spins depends on the amount of supersymmetry and also on how BPS your operators are. Your external operators are the ones that exchange the guys. So I should have clarified here after Philip's question that the spectrum I was drawing was precisely in the OP of these two scalars that I'm studying. I know that there will be operators of dimension delta and spin L. Maybe put it like this, with OP coefficients. This was technically true, but not what I wanted to do. That have OP coefficients that are smooth functions of the spin, and then some operators whose dimensions are smooth functions of the spin. And I just need to sum over well, the spins and different Regge trajectories. So there will be different trajectories that I will put an I here. And so there will be other trajectories like this. So this was just a highlight. I will now unpack this and explain where this comes from. So what I will focus on in this talk is the 4-point function of stress tensor multiplets in this n equals 2,0 SCFT. Stress tensor multiplets because they're the most universal, they're the thing I'm guaranteed to have there in any local theory. And thanks to supersymmetry, I will get away by studying scalar correlators because they are related by supersymmetry to the stress tensor. And then combining analyticity and spin in the sense that I just sketched and supersymmetry, we get that all operators must lie that appear in this correlator must lie on Regge trajectories starting at spin -3. And then demanding the two things together, we will find intricate relations between the trajectories of unprotected and protected operators. So for example, we will see that a long multiplet at spin -2, and this is why I was insisting on keeping a negative spin, should actually match, should actually give you the stress tensor multiplet. So a short trajectory, a short operator must lie in the end at the negative spin of a unprotected long trajectory. And once again, because this whole thing works for any spin, then the inversion formula, which I will now introduce, gives us a way to try to use some iterative procedure to bootstrap the 4-point function by starting with some trial spectrum, inverting, see what we get, plugging back the result, and repeating this procedure and see if a fixed point is hit. So this is what I will end by showing some preliminary result on. So this was a quick highlight, but now I will put in the details. So I will start by discussing the analyticity spin, or reviewing the analyticity spin, the work of Simon Carnot. So for this, no supersymmetry is needed yet. And the idea of the story is to obtain an inversion formula for the OPE. So if I take a correlator of 4 identical operators and scalars for simplicity, and this is the correlation function that depends only on 2 cross ratios after I multiply by this prefactor that carries the weight. It has a decomposition like so, as a sum over all the spins, and an integral over dimensions, where here we're integrating over these complex dimensions. So in the delta plane here, I'm integrating along this line. And I'm integrating a function that has this C delta L, that has poles where the operators are, and whose residues are proportional to the OP coefficients, such that when I deform this contour, I end up picking up the poles of, I end up picking up the operators as the poles, and I recover my usual OP by closing this contour to the right. And here they are just the normal conformal blocks that you decompose your correlator in. And in doing this, there are some non-normalizable contributions that need to be taken care of separately, but they won't play an important role in this talk because they're not there in the supersymmetric case. And so the whole point of writing the correlator in this more complicated looking way is that now the CFT data is all packaged in this function here. And the statements, when we say that the CFT data is smooth in spin, what the statements we're really making are about this function C delta L and how it behaves with L. So these blocks and the way we went into these complex dimensions is that now we have a complete basis and we can use orthogonality of the blocks to extract this function by integrating. So we reach the Euclidean inversion formula, where we integrate against some kernel the 4-point function in an Euclidean configuration. And here I'm just putting 1, 2, 3, 4 as subscripts to remind you of the positions, not because the operators are different. And so now this formula gets for you this OP density of operators. And this is an old result. It basically amounts to the OP decomposition. It's only valid for integer L. And you actually need to know the whole correlator to get anything out. To get this function, you need, if I give you the whole correlator, you can integrate against this kernel to get out the CFT data, or you could have equally well just expanded in blocks with Mathematica and pick out the coefficients. Now, what Simon did was to start from this equation and manipulate this integral, this kernel, to end up in a Lorentzian inversion formula, where you now integrate in a Lorentzian domain against some modified kernel. And instead of the correlator, you only need to know the double discontinuity of this correlator that I will define in a second. So now the nice thing about this presentation of this function C delta L, it's just a manipulation that went from one to the other, but now you have a function that it no longer requires integer L. So this is in the sense we say this is analytic in the spin. So we found some analytic continuation of the CFT data, or more precisely of this OP density function. In these manipulations, some arcs were dropped, some integration arcs when we deform contours. And this is where this condition of spin bigger than 1 comes from. you need that the correlator goes to 0 fast enough in the region where you drop the arcs, and you're guaranteed to have that in a generic CFT if this happens. If you have SUSY, then the correlator behaves nicer, and then you can have analyticity down to lower spin. And this ingredient that I introduced here, this double discontinuity, is what I will now define. So for that, let me start by reminding what these cross ratios can mean physically. So you can use conformal symmetry to put your 4 points, your 4 operators on a plane, and you can put one at the origin, one at 1, and one at infinity. And the last one you can put at position ZZ bar. And so these are the ZZ bar cross ratios I have here. And then if you go on the complex Z plane, so let me remind you here that Euclidean signature would mean that Z and Z bar are complex conjugate. But when we massage the contour to go to Lorentzian, they become real and independent. And in particular, the integral we have is in this region between 0 and 1. And the double discontinuity is simply the difference between the correlator evaluated here, which is this guy, and the correlator evaluated after going through this branch cut at the same point and going through the branch cut in the other direction. And these are what these two terms here are. So these double discontinuities, these are operation that you can also write down as a double commutator. And it has some nice properties, as we will see in a minute. So what have we done? We now have written this OP density as an integral in the Lorentzian region of a double discontinuity of the correlator. And now the nice thing is that I no longer need to know the whole correlator to get some information out. So in this, we get to represent the correlator through its T channel. So through the OP between guy number 2 and 3, the middle ones. So let me maybe go back here to emphasize that the OP I was inverting, the OP I was writing down here was the 1-2 OP. So I was doing this channel. We invert this OP, we go through this massaging, and we end up with this expression. And now we need to compute this double discontinuity. And we can compute it by resorting to the other OP, the T-channel OP, which is between the two middle guys. So doing this instead. And we are getting information about the S channel, which was this OP. So this has to do, the fact that you're required now to go to T channel has to do with the fact that the double discontinuity of a single S channel block actually vanishes. So you'd actually need to resum. The two procedures don't commute. The double discontinuity does not commute with the S channel, but it does commute with the T channel. And then, as I was saying, this double discontinuity and this inversion kernel more generally has some nice properties. One nice property is that if you take the spin very large, the kernel actually projects the integral to a limit where this operator is approaching the light cone of number 3. So it's the T channel that's dominating, and moreover, these two operators are approaching each other's light cone. And we know that in this case, the OP is actually dominated by low twist exchanges. So at large spin, low twist dominates. And this justifies a lot of work, or puts on a firmer footing a lot of work that had been done in the light cone bootstrap, where people were matching those large spin in one sector with low twist in the other. And the other nice feature is comes when you want to study perturbations about generalized free series. And this comes from the fact that this double discontinuity operation actually gives 0 if you evaluate it on operators that are exact double twists, the type of operators you get in a generalized free series that are just the external operator, some box to the n, and then a bunch of derivatives. So if you're in a generalized free series, all of these operators don't contribute, and the double discontinuity is 0. And then as you do perturbations around generalized free theory, these operators will all acquire an anomalous dimension. And the double discontinuity of a block with a small anomalous dimension actually goes like the sine squared. So you see that the anomalous dimension only kicks in at order gamma squared if gamma is the anomalous dimension, and this allows you to do some perturbation theory at around 3 points. So you have finitely many operators having non-zero d-disk, and you have a starting point for your expansion. And this has been done. I didn't give references because there would be too many to fit on a slide, but it has been done a lot in large N series or large central charge, and also in the epsilon expansion. And it gives very nice results. The only downside is that if you're now doing this inversion game order by order in some perturbative parameter, the inversion formula actually works for less spins, and it has to do with the fact that the nth order correlator behaves worse in this limit where the arcs were dropped. And so you cannot drop the arcs for all spins down to spin 1, only down to some number that grows as you increase the order. So you start getting more and more low spin ambiguities. So maybe here is a good point if people have questions about the inversion. Okay, then I will just give a little comment on where the rigidity comes, this rigidity in spin, on how operators end up being related, being so rigid. And this has to do with the Regge limit, and this is also why these are called Regge trajectories. So the Regge limit, going back to this plot I had with the cross ratios, it amounts to taking one of the cross ratios around this branch cut and then sending both to the origin with fixed ratio. And the 4-point function was shown by Simon to be bounded in this limit. But now if you look at the single S channel block, you will see that it actually grows like this. And here you see y the spin -1. So you can add spin 0 if you have a nice 4-point function and you start adding S channel blocks. You can add spin 0 and spin 1 blocks without ruining this nice boundedness in the Regge limit, but you're not allowed to play too much with the spin 2 or higher operators. So this is the source of this rigidity, and is also why it's worse in the perturbative expansion, because the Regge growth of the correlators order by order in 1/n, say, gets worse. Okay, if there are no questions, then I will now add in, oh, okay, I had just one picture, but I already, what I already drawn in the beginning of now this gives us this picture of Regge trajectories. So I know that the O1, O2, OP will have operators that must lie on some trajectories, and I only drew them starting at spin 1, and the operators are here in these intersections, but we're saying that the CFT data can actually be continued in spin in between. So now if there are no questions, I will move on to adding supersymmetry. Okay, so now changing gears, our target will be 6-dimensional n equals 2,0 SCFTs. So these are the maximally supersymmetric series. They have the maximum amount of supersymmetry in 6 dimensions, and they're also the maximum amount of dimensions where you can have a superconformal algebra. And they have 16 supercharges and Poincaré supercharges and 16 conformal supercharges. These series are quite old. They were found in the 90s as various decoupling limits of string and M theory, but we still know very little about them. Despite that, they play a central role in the sense that many lower dimensional series can be obtained through the compactification of these series. And many dualities can be understood also in this way. But they have no Lagrangian description available to describe them. So the descriptions we have are stringy in nature. From those early works, we also know that they have an AD classification. So they are classified by simple and simply Lee algebra. And we know the central charge, by which I mean the two-point function of the stress tensor of this theory. So in particular, as the simplest example, if you have a stack of n M5 branes, the low energy effective theory on them will be the AN-1 SCFT plus a decoupled free tensor multiplet. So these series are isolated fixed points. They have no exactly marginal SUSY preserving deformations. So they're really isolated series, which is also one of the reasons we're going after them with this approach, because there are no, if you fix the central charge, you expect one theory there and not a conformal manifold worth of them. There is a protected subsector that is also written down in this paper, and that fixes infinitely many OP coefficients. So I call the operators that are captured by this chiral algebra the chiral algebra operators. And we know from the start what their OP coefficients should be. We also did some numerical bootstrap on this series, and they have been extensively studying in 1/c expansions in this list of papers. So I'll be comparing the results with these last 2 points. So what does the spectrum of this series look like? So here I will be studying this series at finite C. This is to guarantee that I have analyticity all the way down to spin -3, and I won't be doing 1/c perturbation. Even though I can take C very large, I will always take it to be finite. And I want to study the most universal multiplet in this series that's always guaranteed to be present. And that's the stress tensor supermultiplet. So the stress tensor itself is related by supersymmetry to this scalar, which is a superprimary of a multiplet. It's a scalar of dimension 4. And it transforms under some representation, SO5, and some representation, which is the 14, of the SO5 R symmetry. So this is the R symmetry algebra of the 60 series. And if you fix the 4-point function of all of these superprimaries, it actually fixes the 4-point function of any operator you find in the same multiplet, including 4 stress tensors, as was shown in this paper. So we lose no information by restricting ourselves just to the primary. And everything we get about the theory comes just from, this is all we have to study in the end. So these guys are scalars, which makes life much easier, but they do transform in some non-trivial representation of the R symmetry, which means that when you take the OP, you'll have operators appearing in all representations that appear in the tensor product of 2 14ths, and I've listed the representations here. So this means we have 6 R symmetry channels. So we'll have 6 functions of the cross ratios if you want to write down this 4-point function. So these R here goes from 1 to 6, labeling all these 6 representations. And each channel will have a decomposition in normal 6-dimensional conformal blocks. And these OP coefficients correspond to the conformal primaries that are exchanged. These are just conformal primaries, not superconformal primaries. And now we have to see how supersymmetry relates them. So this was done by Dolan, Galou, and Sokachev. And they worked out all the constraints of supersymmetry. And they determined that all these functions are fixed by 2. All these 6 functions are fixed just by 2 functions. One function of the 2 cross ratios, Z and Z bar, and one function of just one variable. So just as a side comment, this H is related to this inherent chiral algebra that you can carve out in this series. And so this H is related to the chiral algebra correlator. And as such, it only receives contributions from this type of operators that contribute to the chiral algebra. Whereas A receives contributions from everything, all protected and unprotected operators. And another nice feature of 6 dimensions is that we can actually impose the series interacting, because conserved currents of higher spin actually sit below the unitarity bound. So it's very easy just to set them to 0 and there are no ambiguities. As I said, this H is the chiral algebra correlator and it can be worked out explicitly. The particular form is not very illuminating. I just wanted to show that it's something we know explicitly and it depends only on one parameter. which is the central charge. Again, it's the 2-point function of the stress center. And from this, and decomposing it in blocks, you get rid of the OP coefficients of all these protected chiral algebra operators. And I will call them chiral algebra shorts in orange. And then A receives contributions not only from these guys that we know, but it also receives contributions from some shorts. They're operators that are protected in dimension, but whose OP coefficients are not known. And then from long operators that can have any dimension above unitarity. And then we don't know either their dimensions or their OP coefficients. And then you can work out from this decomposition of these 6R symmetry channels through their relation to this A, and this relation is through differential operators. You can work out how this A looks like, and it turns out to admit a decomposition in something that I will be calling superblocks. But they are not particularly complicated. They're just normal 6-dimensional conformal blocks with some shifts here. I shifted the dimension by 4, and this here is, they look like blocks of a 4-point function of operators with unequal dimensions. So this here is delta 1 minus delta 2, and this is delta 3 minus delta 4, considering a 4-point function of 1 or 2 or 3 or 4. So even though I'm looking at the 4-point function of 4 identical scalars, the super blocks end up being normal bosonic blocks with these weird shifts. But because this is all there is, you can we can mostly use the inversion formula I just reviewed, now applied to get this OP density here that will capture everything, shorts and unprotected operators. And the claim that we show in the paper is that the CFT data that contributes to this function is actually analytic in spin for all spins, starting at spin for all positive integer spins and actually below, and starting at spin bigger than -3. So this is shown by taking Simon's inversion formula and adapting it for this supersymmetric case. There are some little things we have to be careful with, but in the end, we get this result. And so we get exactly the type of inversion formula wrote above. And now we can ask what contributes. So we get the CFT data that contributes here in terms of some integral of a double discontinuity, and what operators contribute to the double discontinuity. Well, from the chiral algebra shorts, most of them don't actually contribute, even though we know them. I only need to know the identity and the stress tensor. Luckily, these non-chiral algebra shorts I don't know, they don't even contribute because their dimensions are exact double twists. So they're protected to be what they would be in a generalized free theory. And then I just have contributions from the generic longs. But if you know this, then you get out everything. You get the guys that didn't contribute as well, and you get everything else. So this is the type of game we would like to play, of seeing how far we can go in bootstrapping this theory, starting from the little we know, getting something out through the inversion, and then plugging it back and see if there's a iterative procedure. But before that, I would like to discuss a little bit more of the analytic structure of the Regge trajectories in the 6-dimensional theory. So because of supersymmetry, we were looking exactly at this function here, that from it you get all the R symmetry channels. So the naive thing would be, I just look at this function and I'm done. This turns out not to be completely correct, but let's start with that. So I want to ask, what's the OP density of this function, and what do the Regge trajectories look like drawing this type of operators that we know there? And this is the picture I get. So I'm plotting here the dimension minus the dimension of the operator minus the space-time dimension divided by half, which is 3. And here the spin. And so this line denotes the operators that are captured by the chiral algebra. And again, the physical operators live at these intersection points of even integer spin. And in between is what the inversion formula gives you. And through other works of Simon Safin and Petr Kravchuk, they can be related to some light ray operators, but I won't have anything to say on that. So this is the first trajectory I find. Then the next trajectory are these shorts that have also protected dimensions. And then I have longs. I have a leading long trajectory and then subleading long trajectories that I just sketched somewhere here. And this starts at spin 0, and it seems that I don't have any use for this lower space, and this is all I can say.
Magdalena?
Yeah, go ahead.
Can I ask a very quick question? I'm sorry. Could you say something about what is the actual physical meaning of the CFT data below below 0 spin?
Oh, that's great. At first we thought there wasn't, right? It's like supersymmetry overshoots and we get analyticity for much lower spin. But in a minute, I will show you how it actually comes about. Okay. Yeah, so that's a great question. I can go on then and I will.
Yeah, that's fine.
So,
if you're that's fine.
Yes, so then at first I was saying we thought this was just too much and we were done. But then we decided to check, just for the sake of it, what happens in all of the R-symmetry channels that you can get from that. And you would expect that analyticity already comes for granted because it's here, right? If my spectrum behaves nicely, it should be fine. So then we look at the Regge trajectories for the singlet R-symmetry channel. And things get shuffled around because now for example, this guy here is a superconformal primary of the leading long trajectory. So it was this guy. But now it comes in this channel. There's not only the leading long superconformal primary, but also all of its descendants that are obtained by acting with supercharges on it. So now I have a bunch of conformal primaries, sorry, like this one, not that one. I have a bunch of conformal primaries that are super descendants, but they appear in this, if I look at this R-symmetry singlet channel, all out. And I omitted many other trajectories. You can imagine that the shorts give a large list of trajectories. I just drew for simplicity the longs, the leading long trajectories. So now analyticity, even though I kept telling it was for spin bigger than -3, in this singlet channel, you've actually max out your luck and it's actually only spin bigger than 1. So again, it's something you can see by how this correlator is bounded in Regge, and this one has no guaranteed better growth. But still, I should be able to look at spin bigger than 1 and see that operators fall on trajectories. And I immediately noticed various problems. So there's this trajectory that seems to end in the middle of nothing here. And it should have continued at least to spin 1. And then there's the stress tensor that doesn't appear in that correlator, but here it's just sitting as an isolated operator. And so the natural guess from this is to say that the stress tensor should actually fit in the closest trajectory, which is the leading long, and it should fit like this. So you should connect these two. And this is just one simple issue, but all other long trajectories will have the same type of issue. So I'm just highlighting one, but there are various issues of this type. And so our claim, based on looking at this, and we also have some data from the numerics to see where these trajectories look. And our claim is that then this conformal primary, that is a supersymmetric descendant, must be continued down to spin 2 here and capture the stress tensor. But now if we translate this to a statement about the superconformal primary, we learn that the leading long trajectory, the superconformal primary of the leading long trajectory, has to extend to spin -2 because it's 2 units down from here, from 4 to 2, where it hits this particular dimension, such that this guy captures the stress tensor, and it has a particular OP coefficient, such that we get the OP coefficient of the stress tensor. So this guy that plays a role here, this descendant, has dimension delta +4, L +4, if this superconformal primary has dimension delta L. So now I get to answer Simeon's question, and the meaning of negative spin is that I'm actually forced to say something about negative spin if I want analyticity in this particular R-symmetry channel, and I want the stress tensor to lie on the Regge trajectory. And now you can go on and do this exercise thoroughly through all the channels, and we do that in the paper. And you find a variety of different issues like these that you have to solve always by continuing trajectories down to negative spin and sometimes intersecting with others. But now I should go back to the picture I had shown just before, where I had only drawn from spin 0. Now I should continue this all the way down to spin -2. And this is the leading, so here is the leading long trajectory that started spin 0, and I just continued it. And it's not a coincidence that I landed it there, because the stress tensor is also captured by the chiral algebra. And from the chiral algebra point of view, it also made sense that it should be the spin -2 operator. This basically means that the stress tensor itself does not contribute to A. It only contributes this H function that captures the chiral algebra. But nonetheless, the CFT density knows that at spin -2, the stress tensor is there. And now I also know that the stress tensor must be in the leading long trajectory and intersecting there. And this intersection is actually such that the two poles cancel and there is no pole there. So the two residues cancel. And it seems to be a feature of all of the other proposed resolutions we have for other issues, that you actually don't end up having poles at spin -2 and you really can continue down. So this is the meaning of what happens at spin -2. It actually plays a role, not only here, but also all the leading long trajectories will have to be continued. Otherwise, that dimension +4, spin +4, conformal primary, the poor guy is alone. So you need to continue it down always to spin -2, and they either intersect here or all these residues just vanish. So the simplest resolution we have is looks something like this. And then these ones have 0 residue or something like that. So this is our proposed resolution. It's a bit hard to test. We tested in the examples we could in generalized free theory and the 1/n correction, but it seems very natural, at least for this statement. This seems like the most natural resolution. And incidentally, this would mean that at very large but finite C, these leading long trajectories, they look straight because they're almost generalized free theory. But then there's a huge anomalous dimension because they have to deviate from the straight line by an anomalous dimension of actually, I think it's -2 at this point, such that they capture the stress tensor. So this continuation to negative spin also introduces large anomalous dimensions at negative spins. Then there are, as I was saying, there are various other issues, and we in the paper we list them all, but I won't bore you with all the, this is the most exciting one. But in a picture, this is kind of the feeling we're getting. So the longs at spin -2 here must capture the stress tensor, which is this guy, but the stress tensor is also captured as the chiral algebra shorts at a negative spin. And then the longs must also capture one of these other shorts, which is the other line I drew. And then there are more relations among the longs. So this was just focusing analytically on the structure of Regge trajectories. Then I will switch gears and go to these wild iterative procedures. So if there are any questions on the Regge trajectories. Okay, then let me now show you our exploratory results on this idea. So let me just recap. The idea is that because we have this inversion formula that gives you this OP density, if you know the double discontinuity with some integral, and we know a lot of operators don't contribute to double discontinuity. So from the chiral algebra short, only the identity and the stress tensor contribute. And these are the lowest twist operators that can appear. And then the one after that is this other short trajectory that actually doesn't contribute at all. So after this, you would only have the long twists, which are smaller. We should try to see if we can find a fixed point by just inputting the simplest input, which is the identity and the stress tensor, and this comes with the coefficient 1/c. So we input the central charge here. We invert, we get everything out, both short and longs. Then we extract the leading longs, and we plug it back in the inversion, and then we repeat this procedure and see if we find a fixed point. And we did find a fixed point. And so we ended up having the results for the leading longs of spin of a few spins. We extracted up to spin 0, up to spin 6, sorry, both the dimension and OP coefficient. And we also get the OP coefficients of these non-chiral algebra shorts. So one point here is that the inversion doesn't know about crossing. So the way I'm imposing or trying to impose crossing in this way is through this feedback process and seeing if I find a fixed point. So what I'm feeding it is exactly what it spits out. And so somehow I've found a fixed point that we hope approaches or describes the solution. This procedure would be well justified if you have very large central charge, because as I said earlier, small anomalous dimensions with respect to generalized free field theory give small contributions at sine squared gamma. So if you have very large but finite central charge, I'm actually not losing so much. But then I will go and do this all the way down to finite C, and we'll see what comes out.
Maddalena, would you expect this to work? I mean, does this depend any on supersymmetry or not?
The reason we chose, so people have been playing this type of games in non-supersymmetric cases like the Ising model, where we have a lot of numerical data that is really very precise. The nice thing here about supersymmetry is that I actually get all the spectrum out, all down to spin 0. Whereas in non-supersymmetric cases, you only get the spin 2 and up spectrum. So you cannot do the full inversion game. Well, you cannot do the full, self-contained iterative procedure. You would need some input, and people get this input from numerics.
Okay.
In this case, I'm completely closed. I have a closed loop. I just put these two very basic operators, and then I just, can repeat.
Okay, so it's just that it's more convenient, but the iterative procedure should work anywhere. Or
the iterative procedure does work anywhere if you supplement it. So for non-SUSY, you need to supplement here the spin 0.
Okay.
By hand, which you need to know by some other means.
Okay. Okay.
And this has been done by, okay, I may forget some co-authors, but at least by Simon Zafin for the 3D Ising model, and then also for the 3D Ising model by Karen Huo. But there's the need to, so the appeal of the supersymmetric case is that it's a closed system. The inversion gives you everything. And we have a large C parameter that at large but finite C, this initial input is somehow justified. It's what you'd expect, right? This is just the strict C equals infinity limit, and then the stress tensor comes in. And at very large C, everything else should be suppressed by this sine squared. And then I'm extracting results for low spin, even though I would know that, the higher the spin, the better my results are, because again, for large spin, only low twist in here would matter. So the things I'm ignoring are also irrelevant. So by looking at low spin, I'm really looking at the places where I'm most sensitive to the things I'm ignoring. So let me show you some results that we got with this. I'm starting by the OP coefficient of one of these protected operators that the dimension is protected, but we don't know their OP coefficient. It's actually a quarter BPS operator. And let me unpack this picture. So here is the OP coefficient of this operator. Here is the central charge to a particular power that makes the scaling nice. So it basically goes like n. And the gray line are numerical results. So these are rigorous numerical upper bounds from the numerical bootstrap. So this whole region is excluded. Then this blue line is supergravity, just a supergravity approximation, which strictly is the leading 1/c correction, but I plotted it here all the way down to very finite C. So this dashed line, vertical dashed line here is the simplest n equals 2,0 SCFT, which is the one obtained by 2 branes. Then this reddish line with the dots is the results of our iterative procedure. And here we write some numbers of the central charge, which is 24 at this point. And here I'm showing 2 results from 1/c perturbation theory that people have actually done in this paper 1/c perturbation theory to higher orders, but because this is spin 0, there are these ambiguities. So for spin 0, they only know these corrections, and subleading corrections, I think they probably even give infinity. They're probably poles if you try to set spin 0. So these are, again, just perturbative large C. So you see that our results, first they hit a fixed point, which was not guaranteed from the beginning. So all these points hit a fixed point, and they kind of go in line with the numerical bound. So it looks reasonable. And okay, in the beginning they match the large C, and then they start to deviate. But naturally, large C should not be trusted at such small central charge. The results work nicer for large C, as could have been expected. For small c, it's not ideal. So here there's these 2 points, and I'm showing these 2 points because this is the fixed point we reach. And we tried, because we know from numerics a much better estimate at this point. So we tried to feeding it in and seeing what it came out. And this is the corrected result. So if you correct it, comes down. But this doesn't end up being a fixed point. You always have to correct it at each iteration, which is also reasonable because all the anomalous dimensions are pretty big by the time you reach the central charge. So our whole procedure maybe shouldn't have been expected to give nice results. And we have a few others. So we have many more plots in the paper, but just to show also a long unprotected operator. Again, it's the same type of plots, the numerical bound, supergravity, and the corrections, the perturbative corrections in 1/c. And then here is this red line is the result of our procedure. And again, the correction for the C equals 25 result. And we can also extract the OP coefficient of the leading scalar, which is here. Again, for large C, it always seems reasonable and in line with the numerics. For small C, it actually stops being a reasonable approximation. It even ends up in the excluded region of the numerics. We would have liked to go beyond. I'm only showing spin 0, and I told you a bunch of predictions for negative spin. But from a practical point of view, this extraction of these numbers just doesn't work for negative spin. So there's a trade-off that we're doing here that I can go into the practical details if people are interested, but we just couldn't get any reliable estimates. These numbers are reliable, these things converge, and we have some trust in the number that came out. But for negative spin, we just couldn't get any reliable estimates for the numbers, so we couldn't check this huge anomalous dimension. This is presumably related to the fact that we're inputting very little. We're really inputting something that is only true at very large central charge to begin with. And anomalous dimensions are very low, very large for spin -2, as I was saying, because it has to shift a lot. So let me wrap up. So these few plots were the first exploration of this wild bootstrapping of the 2-0 series with inversion. This is really just a preliminary work. To do it seriously or more thoroughly, we would need to incorporate better numerics, add subleading trajectories. We were only feeding back the leading long trajectory. And the other thing we were agnostic about was the distinction between the AN and the DN series. So we would need to try to see 2 fixed points, perhaps by incorporating the leading coefficient that people got when doing 1/c perturbation theory. Perhaps we could use that as a way to tell this iterative procedure if we're looking at the AN or the DN series. That if I go back to this plot, sorry, here, you see that they have slightly different dimensions, but our procedure just converges to a single fixed point. We don't know which it is. And then the other thing would be a bit more speculative. It'd be nice to try to incorporate the structure of Regge trajectories we saw somewhere to make use of this negative spin. Especially in the numerics, it would be wonderful if we could find a way to fix. We know that all the trajectories have some pin points at spin -2, and it would be wonderful if we could just pin them down. And more broadly, all the work on supersymmetric dispersion relations that people have been doing for supersymmetric series, you would need no subtractions. So they would also be appealing there. And let me just end by saying that the first part, the structure of the Regge trajectories in supersymmetric n equals 2,0 series, it actually should look very similar in many other supersymmetries for dimension n equals 4, n equals 2, etc. So this type of structure of negative spin will prevail in, this was just one example, but it will be there for others. And I will end here. Thank you.
Wow. Wow, very, very wonderful, very impressive results. Are there questions for Dr. Lemos?
Can I ask one question? So the long multiplet that you're talking about, which like adjoins, which like hits the stress energy tensor pole, what are they? What is it in the supergravity regime? Are they like a multi-graviton states?
Yeah, so in the leading long trajectory, it
Right.
would be the double trace operators. So they would be, yeah, exactly those. That's why I was saying that the anomalous dimension should be huge, because they should be asymptoting to a different number at large C. And at very large C, they should be pretty much a straight line.
I see. So
actually,
like
you can see it. You can see it here. So this is a supergravity. They should be going to 8 at spin 0. And the numerics are slowly converging there. And then I'm saying that from spin 0 to spin -2, it has to go down by like -4. So 2 units of spin plus the 2 anomalous dimension.
Otherwise,
sorry. So one graviton state like merges to the 2 graviton states from the point of view of supergravity then.
Yeah, so it's, yeah, so the type of operators I'm looking at would be something like, well, trace, I don't know what, in n equals 4, they will be, you know, trace O squared, trace phi squared, and then the double trace operator made out of it. But here, yeah, I shouldn't, there's no gauge group, so I shouldn't really.
Thanks.